Hey folks, Adam Ward here. I want to talk to you today about how we design an aeration basin as part of the activated sludge process. Okay, so just to remind us, our focus here is on designing this aeration basin as well as the recycling of some of the outflowing microbial biomass back to the inflow. We're not going to focus specifically on how to design a secondary clarifier today. We've already talked a bit about settling basin design in previous lectures, and so that all would apply to how we design something whose purpose is settling of constituents in water. Okay, so we're going to use this image a few times today, and so I wanted to just make sure we're all on the same page here. This is about coupling together three different mass balances. One is a mass balance on the flows of water, so we'll use Q's there, our volumetric flow rates. One is a mass balance on biomass, which we'll represent by an X, that's a concentration. And one is a mass balance on substrate, or the food source for the biomass, the BOD that we're putting in, and those will be represented by capital S's. Additionally, we've got several ins and outs to keep track of. So I just want to point out the nomenclature I'll be using today. Influent, so what comes in to the secondary treatment process, you can see has a subscript I. The return flows in purple have an R, so QR and XR represent the returns. Effluent, meaning what leaves the secondary clarifier, go with an E. And then down in the bottom right, where the image says WAS, that's waste activated sludge, and that has a subscript W. And that's referred to here as wasted because it's biomass that you produced, but you don't have any use for it. All you're doing with it is sending it on out of the system. So that's how much biomass is being wasted from the perspective of this unit process. Now, in general, that's not a bad thing. We're trying to create that biomass to pull the BOD out. Okay. So we're going to step through this. I want to show you a bit of where these equations come from and why they exist before we just pull on some of the most useful ones for design. So the first thing we'll do is establish a control volume around this entire process. So one input and two outputs, and we'll do a mass balance on biomass. And so on the left-hand side is our time rate of change of biomass in the system. Is equal to, we have one inflow, the influent in this case, QXI. We have two outflows, the term here being the effluent, and you can see that the amount of discharge leaving is Q minus whatever Q goes with that waste activated sludge. We have a third outflow, or a second outflow, a third term, which is the waste activated sludge. And then the last two terms here represent the growth of biomass within the aeration basin and the decay or ultimate death and removal of biomass in the second term. So those take the monad kinetics that we looked at in the previous lecture and put them into this KVC format that we've used on our mass balances before. And again, all of those terms have units of mass of biomass per time. And we can go ahead and simplify this equation a little bit. We can assume that we're operating at steady state. We can reorganize. And you'll notice I've made the assumption here that the biomass that is coming in, so X, it should read XI, and the biomass and the effluent are negligible. You don't have to do that, and in several slides here we'll kind of pull back around and look at what this would be if you keep those terms. For simplicity to derive this, I'm going to drop those, but I'll show you later where they would come right back in. And so sort of the key equation we get to here is written at the bottom now, where we've got all of our substrate terms on the left-hand side and all of our biomass terms on the right-hand side. And we're going to just set this mass balance aside for the moment in this format. So mass balance for biomass is done. We'll do the same thing for substrate with the same control volume. And this looks quite similar. We've got our time rate of change of substrate on the left is equal to inflows minus the waste the waste term minus the effluent term. And then here we've got the term that describes the use of substrate. And what you can see in there is sort of that first term in the right-hand most term there, the mu max S over Ks plus S. That's sort of acting like the reaction rate. That's how fast we're using up substrate. The 1 over yield times substrate is actually equivalent to the biomass. So we're kind of doing a unit conversion there, if you will, and then the volume. So this is a KVC term, just like we've seen before for first order reactions or first order like reactions. And this is describing the loss of substrate and the appearance of biomass. So that actually couples together these two equations. And again, we could assume steady state, we can reorganize ourselves. And if we put all of our substrate terms on the left, or many of our substrate terms on the left, I suppose I should say, and on the right-hand side, we separate out our inflowing Q. I guess I've used a Q naught, that should be a QI for completion, and those S's should be SEs. We get this simplified equation. So from the previous two slides, you may notice both of the equations that we got to have the same terms on their left-hand side. And so we can actually combine those two together. And so this is really handy. This gives us one equation that describes our design, and it's got virtually none of the kinetics stuck in it. Right? This relies on knowing something about your inflows and your outflows concentrations, but it doesn't rely on the underlying kinetics of the equation at all. And so this can be a handy design equation. All the terms here should be known, specified, or something that you can derive from a laboratory test, and this is a great equation to use to solve for volume. Okay. Also in the design process, we want to keep track of how long the biomass spends in the system. This goes by several names. People call this solids retention time, SRT. They call it sludge age, or they call it mean cell residence time. And all of these are used interchangeably. And what they're asking is, how long does a microbe actually spend within this system? And so we've done this before, right? These characteristic timescales are about how much of something you have in the numerator divided by how fast you're removing it in the denominator. And so in this case, how much X do we have? It's the volume times concentration of biomass. That's how many microbes. And there are two ways they're removed. One is with the effluent, the left-hand term in the denominator, and one is with the waste-activated sludge, the right-hand term in the denominator. And this is often abbreviated also with a theta C. So theta and that subscript C to describe sludge age. If you made the same assumption that I made earlier about the effluent biomass concentrations and the influent biomass concentration, Xi, then this term would look as I've shown here in orange. Now, what is important here is this is the inverse, or 1 divided by what we've had on the left-hand side. So it's flipped over. So we can actually take this definition of solids retention time, and we can relate that to the equation we had drawn on the previous slide, that we had written on the previous slide. So this equation, again, is very helpful to us in design because it links together several of the variables that we care about. And just to reemphasize again, that theta C, solids retention time, SRT, sludge age, mean cell residence time, MCRT, Those are all interchangeable terms for the exact same description, which is how long does a microbe spend inside of the system. Okay. One last important thing we want to think about here in design is what's called washout. And so you can imagine a case in which your system is so small that it's actually being flushed out before the microbes have a chance to grow. And so in that case, you would basically be creating this flow-through system, but your aeration basin won't do anything. It won't actually achieve treatment because you don't give the microbes enough time to reproduce. And so we can take one of the equation from the previous page and say, well, if that happened, effluent concentration would be the same as inflowing concentration of BOD. You wouldn't get any net removal. And so you can actually use this to check yourself on what is that minimum theta C, or what is that minimum solids retention time that I need. In general, design will occur by calculating what that minimum would be and multiplying it by a safety factor. Mine suggests that might be anywhere from 2 to 10. Other literature has suggested that may go anywhere as high as 70. But the idea here is that we want to create a system where we're giving microbes more than enough time to reproduce. It's critical to our treatment that those microbes have a chance to reproduce, to grow new cellular material, and actually use that substrate that we're providing. So, just to summarize a handful of important design equations that we want to think about. We can take the equations developed in these last handful of slides and solve them for quantities that we might be interested in. For example, the equation written here in the top left can be used to estimate what is the effluent concentration of BOD. And that's pretty important because that's likely a value that's permitted in our NPDES process. Our solute or solids residence time, our SRT, we saw this just a few slides ago, but again here in summary, that becomes a critical value for us. And X, and again that's the concentration of biomass in the aeration basin, that's something that's going to be of particular interest to us. In general, X is something that we might specify so that we'll know about the concentration of biomass we'd like to maintain. We don't want too much to get into this overcrowding problem. We don't want too little because it would be inefficient. And you'll see I've noted there in red, that's a TAW on the bottom. That's our hydraulic residence time. So all of these are versions of the equation we looked at previously, but reorganized to solve for some of the variables that we're interested in. All right, a handful more considerations that we might want to keep in mind as we're going through the design process. One is what's called food to microorganism ratio, often listed as F divided by M. And this food to microorganism ratio is describing to us basically how well fed are the microbes that we're growing or cultivating in the system. And so on top is the rate that BOD is being supplied. That's a volumetric flow rate times inflowing BOD. And in the denominator, that's the microbial biomass, volume divided by microbes per unit volume. And this F over M then has units of 1 over time, and this is broadly used as a design parameter. So you can either specify your target food to microorganism ratio, or you can check it against typical values to make sure that you're within a range that we expect to be functional. If you design a system that has a food to microorganism ratio that's too low, in general, your microbes are going to be starved. So very little food, lots of microorganisms. You will get rapid uptake. However, what that means is that you're going to ultimately need either a smaller discharge or a larger volume to achieve the aeration times that you need. And we generally know that these microbes will settle quite well. On the other hand, a high food to microorganism ratio is a system that is saturated by nutrients and you'll get slower uptake. This might allow you to have a shorter residence time in the aeration basin, but these microbes or this biomass is likely to not settle quite as well. And so what we want to think about there is being within a typical range for a food to microorganism ratio, or using it broadly as a check. In our potpourri of things to keep in mind, next up is settling of microbial biomass. And apologies for the slides flicking back and forth here as I'm narrating. I'm having a little trouble with it today, but we'll roll with it. When we want to think about how well our biomass is settling, what we'll typically do is take a 1 liter graduated cylinder, and we'll fill that with our mixed liquor. We'll let that set for 30 minutes, and then we'll actually measure the volume of biomass that has settled out after 30 minutes. And so you would read where that red line is on the graduated cylinder. And we use this to calculate something called a sludge volume index. And the idea here is we want to know what is the volume of sludge after we let settling happen for 30 minutes, normalized to the mixed liquor suspended sediment concentration. So this will come out in units of milliliters of sludge per grams of suspended solids that you put into the cylinder. And in general, a sludge volume index in the range of 50 to 150 would be an indication that you're producing sludge that has good settling characteristics. Now, we've been assuming through this process that our sludge would be produced sort of irregardless, right? We will have microbes, they will exist, they will grow and reproduce and generate biomass. One of the things that we can do is ask how much sludge is produced, and you can estimate that as this px, and that would be in mass of sludge per day, for example. But we should double check that we have the sufficient ingredients, if you will, or the nutrients that we require in order to allow the microbial biomass to grow. So we need to basically check that we can create biogeochemical conditions that will let our biomass continue to thrive. We do this in a few ways. One is we design for a mixed liquor volatile suspended solids concentration that's low enough to keep us out of that range where we expect to hit the carrying capacity and slow down the growth. Additionally, we do like to check and make sure that there's enough of each of the major nutrients required for those microbes to actually produce new biomass. And so if we take a typical microbial biomass of approximately 60 carbons to 87 hydrogens to 23 oxygens, 12 nitrogens to 1 phosphorus. And you could think of that as sort of a Redfield ratio for microbial biomass in these basins. We can use the stoichiometry there to find out that we need to have about 0.112 times that sludge production rate of nitrogen coming into the basin. And similarly, we need to have about 0.023 times that sludge production rate of phosphorus coming into the basin. And so these are simple checks, but if we are not providing enough nitrogen or enough phosphorus into the system, we're going to inhibit microbial growth, or perhaps we'll favor the growth of a different organism that won't settle as well. That'll produce, small flocks that won't settle out in our clarifiers. And so, not only are we trying to control the physics and control the biogeochemistry here, but we're trying to create the right conditions to grow the microbes that are optimal users of that BOD and that are going to settle efficiently for us. And so making sure that we're not limiting them on nitrogen or phosphorus is a common check that we might need to consider. Just to give you a sense of what some of these ranges look like, the ratios of BOD5, so 5-day biochemical oxygen demand, to nitrogen to phosphorus go anywhere from 100 to 5.4 to 1. That's BOD to N to P for something that's got a relatively short solids residence time, to 200 to 5.4 to 1 for something with a relatively long solids retention time. So the short summary on this slide is: 1, you can estimate how much sludge is going to be produced in a daily basis, and 2, you can understand how much nitrogen and phosphorus are required to complement or to make sure you're not inhibiting the amount of growth in your basin. Second to last here, oxygen demand. One of the key things that we're doing here is we are aerating this basin to promote microbial biomass growth. And so we want to keep the dissolved oxygen in this basin above about 2 milligrams per liter at all times. That'll keep our aerobic microbes being favored, and those are the ones that are going to grow the most efficiently for us. So, how much oxygen do we actually need to provide? And this is an equation that comes out of our textbook, although we could work our way there stoichiometrically if we wanted to. But this describes to us the amount of oxygen we need to provide as a function of what we know about the carbonaceous BOD and the nitrogenous BOD in our system. And so those first two terms are basically taking discharge Q, using that to scale how much of your substrate S was removed. So Si minus Se gives you how much substrate was removed. And then that 1 minus 1.42Y, that's basically converting that substrate into its effective oxygen requirement. And the next term is asking about sludge produced that had basically died and settled out within the basin. And then that last term is the NBOD, and we can estimate that as discharge multiplied by TKN multiplied by 4.57. TKN is total ketyl nitrogen, and in this case that's a form of nitrogen concentration. It's basically the bioavailable nitrogen when we've decomposed the organic matter. And that 4.57 is the smashing together of several stoichiometric terms that describes the oxygen that it takes us to convert those ammoniums that'll be formed from decomposition into nitrite and ultimately into nitrate. And so this is important to know because in order to keep the biogeochemistry of the aeration basin where we want it, we need to make sure that we're providing sufficient amount of oxygen into the system. Okay, finally I want to look at the recycling rate. And so what we're specifically asking here is, how do you know how much you're supposed to recycle? Right? Who makes the determination of what is the right amount of sludge to send back around the system and back into the aeration basin? So there are two ways that we can do this. One is we can look at the ratio of return flow to the total flow going through the aeration basin. That's QR divided by Q plus QR. And we can approximate that as the same ratio of sludge volume after settling. That would be from that graduated cylinder settling test per liter. The second way we can do this is a mass balance on the secondary clarifier. And so think about a mass balance on the control volume that I've drawn in red. So we'll do this in terms of biomass. We've got basically three terms here. So on the left-hand side, time rate of change. On the right-hand side, we have our inflow of biomass. And then there are two ways that biomass leaves. One is through that return flow, QR, and the other is with the effluent. Now, if we assume that this is at steady state and that biomass in our effluent is functionally zero, and that's likely to be the case because we're highly limited in our total suspended solids, so we wouldn't want to be bypassing that secondary clarifier with much of our particulate material like biomass. We can simplify this relationship down to the ratio of return flow to influent, so QR over Q, as X, that biomass concentration in the basin, divided by the return flow concentration minus the basin concentration. Now, we don't know what XR is, but we do know that an upper limit for it can be approximated as 10 to the 6th divided by that sludge volume index. So that's a 10 raised to the 6th power in the numerator, sludge volume index in the denominator. And so we can use this equation, QR over Q equals X divided by 10 to the 6th over SVI minus X, to actually estimate that return flow QR. And I'll note what you're doing here is you've approximated this as the maximum return flow rate. And so what that means is you're figuring out here what is the minimum return flow that I ought to keep. All right, folks, I hope that helps. There's quite a lot of variable soup going on here, but we will try and talk through that in class and get everybody straightened out on exactly how to go through the design of one of these. Thanks all.